I am Ayman Rehan, a student of MSDS at IBA. Today I will be presenting my Machine Learning 1 semester project, that is Store Sale Forecasting Model. So before going into the analytics part, I would first like to explain the objective and purpose of this project. The dataset that I am using for this project is the dataset of Rossmann. Rossmann operates over 3,000 drugstores in 7 European countries. Rossmann store managers have a task of sales prediction. They have to predict sales on daily basis, 6 weeks in advance. The objective of choosing this specific retail dataset was to create a persona of a store and to forecast the sales of each store separately. The deliverables that I have made for this project are complete understanding of the store behavior, predicting how much a new customer will spend in a newly opened store based on the historic performance of already open stores, testing hypotheses extensively, forecasting sales based on a variety of ML models, assessing the performance of the model used. The corporate domain of the project is retail. Retail of particularly goods that are sold at stores that are widespread, having a daily customer count ranging from 5,000 to 10,000. Some important background knowledge about this domain and data. The domain is of retail where the main focus lies in predicting sales as accurately as possible so as to avoid stockouts, help in production budget planning, and in revenue management. The data I have is of 1,115 stores that are selling products across Europe. I have the daily sales for about 2.6 years of each store, together with the basic information about the store model and assortment type that is defined as basic, regular, extended. Each store can be of one of the types. So one dataset has store pertaining information 1,115 rows, and the other dataset has the store sales data together with the promotion, holiday, and other features that affect the sales of the store. The main objective is to study this particular dataset in detail to drive some common behavior in retail industry, that is the impact of competition on sales, the impact of promotions, etc. The main motivation is to study as many machine learning models that can be used for forecasting and predicting demand for the next 6 weeks of the store. So I will briefly go over the dataset description. Rossmann store data has these features: store type, assortment, competition distance, competition open since here, promo 2 since week, promo 2 since here, sales unit, promo 2 interval. Rossmann sales data has these features: open, promo, state, holiday, store, day of week, date, sales, total customers. So as a data scientist, the problems that I felt that could be solved from the given data, helping us to understand the data better and helping us to forecast in a more informed way are: so the first business problem that I have identified is predicting the average consumer spending given the store attributes. So given the relevant data of sales and the stores, I have created a KPI that measures the average consumer spending. Now, for a newly opened store, based on the attributes, one can predict on average how much a customer will spend. Once we know this and we know the size of the consumer population in that area, we can have a rough estimate of for the average sales of a newly opened store. Regression techniques will be used for the prediction. This is the dataset description. Most of the terms are self-explanatory. Some of the terms that might need explanation are competition distance, the distance in meters to the nearest competitor store. Competition open since month gives the approximate year and month of the time the nearest competitor was open. Promo indicates whether the store is running a promo on that day. Promo 2 is a continuing and consecutive promotion for some store. 0 store is not participating, 1 store is participating. Promo 2 since year week describes the year and calendar week when the store started participating in Promo 2. Promo interval describes the consecutive intervals Promo 2 is started, naming the months the promotion is started anew. February, May, August, November means each round starts in February, May, August, November of any given year for that store. So here I've imported some of the basic libraries that I've used in this notebook. These are 3 of the templates that I have created. The first template is the ML template, which has the functions for Wrangling. The second template is the template which has the functions for regression, and the third template has the functions that is dealing with date time features, as well as it has the time series models. So here I've loaded the data, store and train. So basically we can see that these are the features that the store data has: store type, assortment, competition distance, competition open since month, competition open since year, promo 2 since week, promo 2 since year, promo interval. So we can see that the store type that we have the most is A, and the assortment type we have the most is also A. So store type basically defines the model the store is following. So basically there are 4 types of model: A, B, C, D, and assortment type is the type of products that are being sold at each store, and we have 3 of them: A, B and C category. Promo interval are intervals for which the promotion starts at each store. So then we can look at the other data set. The features for the other data sets are the sales features, that is the day of week, date, sales, customer, store is open, does the store offer a promotion, state holiday, school holiday. So basically this train data set has all the store sales and has 9 columns. So our first step was to get the KPI according to which we can understand the average sales per customer for each store. So for that we first extracted the date time features from the date column. CTF is a function that I have created which extracts the features like quarter, is month, year, day from the date column in the dataset. So after extracting these features of year, month, day, day of week, number, quarter, is month, start, what I did was, here I have grouped it by store, year, sales and customer, and I have summed it. After the group by, I get some sort of this data where store represents the number of the store. Sales 2013 represents the sum of sales that took over store 1 in the year 2013. Same goes for 2014, 2015, and this is the customer count, yearly customer count for each store. So this is necessary for me to create the KPI that I could join with the store data. So here basically new features and KPI added to store data for further analysis. So basically these features have now been added to the store data so that we can conduct our further analysis. So the first part is to deal with the missing values. So we can see that we do have some missing values in competition open since month, competition open since year, promo 2 since week, promo 2 since year, and promo interval. So we can see that we have like 48.8% values missing for promo interval, promo 2 since year, promo 2 since week. We have like 48% of the values missing. Competition open since year and competition open since month, we have 31% missing, and we have only 3 values missing for competition distance. So here what we can do is that we cannot really drop all the columns because it might not be a sensible approach, because either dropping the columns or rows will be losing a lot of information. So what we can do is that for the years that we do not have, we can like put 2025 in it, and for the month which we do not have, we can put 13 in it. So we know that that these are the values that are unknown. And then for competition distance, we can just roughly put the mean value over the data, and then for the rest of the values that are left, that are promo values, we can put a 0, because if we do not have the relevant data, so probably there is no promotion that was in place for these stores. So we can easily put a 0 that is being replaced over here. We can see the shape of the data set that we have created. It has 1115 rows and 16 columns. So here we are creating a further set of new features in KPI to understand each store's persona better. New feature which tells us the number of years the competition has been opened from. We are taking the difference between competition open since month. So basically what we are doing over here is that we are taking the timestamp of now, and then we are subtracting it from the time that the competition has been open, so that we can find the difference between the years and see how long the competition has been open in terms of the years from now. Doing so, we have a new column over here, that is MSDiv, so it shows 13 years, 14 years, 15 years, 12 years, 6 years, 7 years. The computation has been open. The next step is to create new aggregate KPIs that will help us for further analysis. So the 3 KPIs that I have identified are mean yearly sales. We are taking about 2.58 years of data, that is 2 years 7 months, figuring it an average yearly sales KPI. Mean yearly customers, and then mean sales per customer. Mean sales per customer is a very important KPI because this is the average amount spent by each customer in general at each store. So this is the creation of the KPI, mean yearly sales. We just add all the sales of years together and then divide it by 2.583 because we have like half year's data for sales of 2015. That is why the figure is 2.583. And then for mean sales per customer, we take the mean yearly sales and divide it by mean yearly customers. So mean sales per customer is a KPI that we'll be using most to create the persona of each store, because the store may have large sales, but that may be because to the large customers it is catering to, and then there may be another store that is performing well but it caters to a smaller number of customers. So in order to avoid these discrepancies that may disrupt our hypothesis, our main focus would be the mean sales per customer for each store. So here we are doing some basic analysis over the new dataset that we have created, which has now 21 columns. Store type assortment, competition distance, competition open since month, competition open since year, promo 2 since week, promo 2 since year, promo interval, sales, customers, difference, mean yearly sales, mean yearly customers, and mean sales per customer. So here we will be looking at the wrangling methodologies. Business questions that need to be answered this stage are: what are the different store categories and how does their behavior vary? How does competition affect mean sales per customer? Does the competition being old affect the mean sales per customer? Does promotion have an impact on average consumer spending? The techniques that we will be used to investigate will be as follows: correlation analysis, ANOVA, chi-squared, crosstab analysis, and blocks plots. Here I plotted the correlation heat map. According to the correlation heat map, we can see that the correlations that we need to further investigate and that are high are competition distance and mean sales per customer, promo 2 and mean spending per customer. So the first question that we'll be answering is: what are the different store categories and how does their behavior vary in terms of average spending per customer? So the two store variables that we have are store type and assortment. We are first checking if there is a relationship between assortment type and mean sales per customer, mean yearly sales and mean yearly customers. According to ANOVA, we can see that statistically they seem to be independent. So if we cannot find the relationship that we were assuming to find over here, then we check if there is a relationship between store type and mean sales per customer using ANOVA. Here again we did not really find a relationship. Thus, as we assume that there should be a relationship, we can create a new feature and check with that as well, which will categorize the store by both its model type and assortment and then check if a relationship exists. Before creating this feature, we can conduct a chi-square test to check if there is any relationship between store type and assortment. So when we check if there is a relationship between these two categorical variables, we can see that there is a relationship between store model type and assortment. This means that the model that the store chooses depends on what category of assortment it is selling. So here we are creating a new feature using store type and assortment and then investigating if it has a relationship with the mean customer spending. We can see that the new feature SA is a combination of store type plus the assortment. We can see that the new feature that we have created has these four categories: AA, AC, DC, DA, CA, CC, BB, BA, BC. A, the first initial is the model type and the second initial is representing the assortment type. So this is representing stores that follow the model type A selling assortment A. This is for instance representing the third one, the store model D, and which is selling assortment type C. The next question that needs to be answered with it is, within the same store model, we hypothesize that different assortment type should behave differently. So for the assortment types within the store, we did not really find much of a difference. So the difference where we found using ANOVA was here. Mean of SA AC is 9.11, mean of SA DC is 11.5649. So the average consumer spending mean over AC stores is lower than DC stores. So here we can see that we are rejecting the null hypothesis and we're concluding that at least one group is different and is relevant to the class. Here we have taken AC and DC and we can see that they are different. We also continue doing this. We find that AA and DA are also different. We say that AA again is lower than DA, like AC was lower than DC. So this means that we can see that DA, the store model D, is generally performing better over all assortments than store model A in terms of average consumer spending. So then we do this for CA and DA as well. We can see that the average consumer spending for CA is also less than the one that is for DA. So the end analysis we can see that within each model, as far as average sales per customer is concerned, it is different for model A and model D, model C and model D for each assortment type. Further can be investigated by seeing the relevant distributions. We can see that the average spending per customer is higher for store model D than the other models over all assortment type. We can also see that model A and model C are operating in a similar way for each assortment type. So based on the above hypothesis, we can further understand the behavior by looking at the box plots. Here are the box plots that have been plotted. According to the box plots, the important things that we can see is that assortment type C has a higher average spending per customer over all models. AC is higher than AA, CC is higher than CA, DC is higher than DA. And we can see also from the box plot again that model D has higher average consumer spending across all models. Store model A for both assortments had lower mean sales per customer than model D for both assortments. Model D seems to be better in this regard. Then similarly, store model C is similar to A, has lower mean sales per customer than model D for both assortments. Assortment C has higher values for all KPIs than assortment A over all assortments. That is, assortment C tends to be more lucrative than other types of assortments. The next business question that we will be answering is, does promo affects average consumer spending? We can use ANOVA to check if there is a relationship between promotion and average consumer spending. So when we test it using ANOVA, we reject the null hypothesis and conclude that at least one group is different and the feature is relevant to the class. Yes, this means that there is a relationship. Now we can further investigate what type of relationship exists. We are assuming stores which have promotions, average consumer spending will be high. So our main assumption is that stores which have promotions will be seeing higher consumer spending. So here we have plotted the box plot. We can see that the average consumer spending is higher in stores where there is a promotion, where it's about 10, and where there is no promotion, it is about 9. So further we can use chi-square to investigate the relationship between store category and it being offered a promotion. So we can see that there is a relationship between the two categorical variables. So the store type and promo to, this means that the model that the store is following, according to that the promotion is offered or not. And then we can also see if there is a relationship between the assortment type and the promotion type. So basically we can see that there is no relationship between assortment and the promotion being offered. We can further look at the cross-tab analysis and see the details of which stores have a promotion and the count of the stores, so that we can get a reasonable view of, for instance, in store type A, half of the stores do have a promotion, half of the stores do not have a promotion. In store type C, for instance, it's similar, half of them have a promotion, half of them do not have a promotion. And then also we can see that the mean sales per customer value for stores which do not have a promotion within the same store model type is less. For instance, it's 8.63 over here, and for stores that have a promotion within the same model type is 9.37. So the comparison over here is very clear. Yes. So the third thing that we will be looking at is, does promo interval has any impact? So basically we are trying to see if there is any promo interval that is more popular than any other promo interval. So we again use the box plot analysis, and we see that there's not much difference between the promo intervals. For instance, January, April, July, October promo intervals, where promo starts in these months, is just a bit higher. It's not a very significant difference. So the third question that we would want to answer is, does competition distance have an impact on average sales spending? So basically, according to the business, the hypothesis that, or assumption that we already have, is that where stores where the competition is further away, the average sales spending would be higher. So we just need to prove it from our data as well, and see if this agrees with our already supposed hypothesis. So basically we do some discretization, and we create a binning variable where I have labeled the store distances in like categories: close by, near, mid distance, far, and very far. The binning has been done for visualization purposes and for better understanding. So here we can see that shops which have competition close by have a lower mean sales per customer than shops which have competition that is very far away. It is very evident that the stores where the competition is furthest, the mean consumer spending is highest. We can also see from another binning graph, where we are seeing that there is almost a linear relationship. We can see that as the distance increases, the mean average distance of the competitor increases, the mean average sales per customer also increases. We can see that where the competition is further, that is like about bucket 8, the maximum mean sales per customer for that store is $15.6867. This clearly shows that as the competition distance increases, average spending increases. So this means that the distance of a competition in a nearby vicinity does affect the average spending for a store. The fourth question that we'll have to answer is that what is the relationship between competition year and sales of a particular store? So our hypothesis is that stores that have been into existence for more years will be a tough competition for the store, and as the number of years the store has existed, the competition store has existed decreases, the average sales per customer will increase. So basically this graph shows the same, that where the competition we created a binning variable. Again, we created 3 buckets so that we can eliminate noise, and we see that as the time period over which the competition exists increases, the mean spending of the customer decreases. So this means that the older the competition, the lesser are the sales for the store. We have applied the clustering technique over here in order to understand the persona better. So we can see that the alto shows that the optimal number of clusters for this data is 7. So proceeding on, we have calculated the silhouette score, the Callan-C score. The silhouette score, the nearer to 1 it is better, so it is kind of reasonable uh, for this data. So basically this is the cluster composition, the mean of the clusters. So we can see that we have 7 clusters over here, and we can see that the cluster 0 and cluster 6, these are clusters which have mean sales per customer is almost the lowest. So here we can investigate further that the competition over here is this from 2013, and here it is from 2019, and then we have competition distance over here is very less, and here the competition distance is very high. So it is kind of showing that in either cases over here this makes more sense because competition is very near and the store is old, so this means that the mean sales per customer is less. Over here we can see that the competition is near, and competition has opened like earlier, but and the distance is also very far away. But this means that for this store there might be other competitors for whose information we may not have. Again, for the for cluster 2, for instance, we have the highest mean sales per customer, that is 11.24. Here we can see that the competition is old, and but the distance is also far away. Also, there is another thing that this is following model B. Store type D has particularly higher sales registered than store type A and C. So this again is confirmed from the persona that store model D is better performing than the other stores other store models altogether, that is store A and C. So up till now we have characterized the store persona to a very large extent. We have seen that which assortment type is the best, that is the assortment type C overall assortments. We have also seen that store model type D works the best in terms of having the highest consumer spending. Also, we have seen that how the promotion affects the mean sales per customer, and how this the competition being close affects the sales. Also, by the existence of the years that the competition has existed, also affects sales. So basically modeling the problem. If we want to open a new store and predict what will be the average spend of a customer, we will need to see what features we will have. For a new store, that is available information would be as provided for each store, that is all the features that can be known from before the opening are the store type, assortment, competition distance, competition open since here, promo 2, promo interval, promo 2 since here, and promo 2 since week will not be known. Obviously because the store has not been in operation right now, it needs to be opened. We can use the derived KPIs SA, that is a combination of store type and assortment, because that will be known. Based on this, we will be predicting the average spend by customer, that will be our target variable. So basically this is a regression problem. As a target variable is continuous variable, we can use binning to discretize it. However, it will be better to use regression algorithms. So the columns that we have now, after the columns that we have derived, so these are the additional columns that we have derived from the training data set. So the features that we will be taking is store type, assortment, SA, competition distance, competition open since year, promo 2, promo interval, mean sales per customer. So before giving it to a machine learning algorithm, we first need to encode the variables, and we do it by one-hot encoding. After in one-hot encoding, these are the features that we have: store type A, store type B, store type C, store type D, assortment A, B, C, and the different combinations, and then promo interval 0, promo interval present or not present, and promo interval for February, May, January, March, June. So yes, so this is a elaborated heat map showing the relationship The heat map shows that we can again see the highest positive correlation between store type D and mean sales per customer. Competition distance and promo 2 can be seen to have a reasonable positive relationship that we have already investigated. We can check for null values. We can see that we had already accommodated for null values before. We do not have any null values. Before giving it into a machine learning algorithm, we perform the screen test split. Over here, after that, we perform regression. The first regression is without feature selection. So this is the result that we are getting. So here we can see the result of regression without feature selection, and we can see over here that gradient boosting according to the root mean squared error is performing the best. The root mean squared error is the lowest, and also the R2, which shows that how much the independent variable is able to capture the variance of the dependent variable, is reasonably the best compared to the other algorithms. Also the R2 adjusted, which shows that how adding new features help us better predict the variance, is also the best for the gradient boosting regression. So gradient boosting regression with feature selection, without feature selection, seems to be the best. We will then be performing the same thing, but now with random forest feature selection. So for this, we can again see that gradient boosting is performing the best with the lesser number of features, but it is still giving reasonable accuracy. The difference between with feature selection and without feature selection is not much. So this is something that one can think about because it saves the computational cost. We can further look into what are the features that have been selected. So basically this is the feature importance table. The threshold is 1 that we have selected. We can see that competition distance is store type D, competition open since year, promo interval January, April, July, October, promo 2 present or not, promo interval 0, that is we do not have the promo interval, and store type B are the most important features in determining the output. So yes, and we can see that gradient boosting is giving 0.48 R2 and 0.47 R2 adjusted, and the root mean square is 1.4. Here the root mean square for gradient boosting regression was 1.37, that was without any feature selection. So we can see that even after selecting features and reducing the feature base, the accuracy of the regression model has not reduced. So depending upon the representativeness of the data set, and if we are looking for a model that does not overfit, we can go for something like random forest feature selection. But if we know that the data set is very representative and we do not have any computational issues, we can we can stick with using all the features for the regression problem. So this is the end result of the first business problem, that was to predict the average sales per customer looking at the features of the store. Now we will be moving towards the second business problem, that is the actual forecast of the daily sales for each store. Now we can move towards the main business problem, that is predicting sales based on the given features and time series models. So for this, I will be utilizing both time series and regression techniques. The notebook has the extensive detail of the methodology and models that I have used, namely regression models, smoothing models, time series models. So we already have the features, so we do not really need to convert this time series problem into a simple linear regression problem, but in order to enhance, we can add features to this regression problem. So the first 3 features I have added are the lag features. As you can see, these are the features that have already been given to us. These are the new added features. Then further, I have added some time features that you can see: month, day, day of week, number, quarter, is month. And here I have conducted an analysis. This shows that the number of customers that visit the store on each day of the week. This shows the sales for each day of the week. We can see that the sales are higher on Monday. Then this further shows that the number of customers coming on days when the promo is being offered is much higher than the number of customers that come on days where promo is not being offered. Simultaneously, we can also see that sales are higher on days where their promotion is available. Moving on, regression has been conducted on 2 data frames. So before we move on, the regression the first data frame that I'm using is the one with all the features. These are the features that I'm using with the new added features, the lag features and the time features. So regression with all the features. This is regression with all the features. Then I conduct regression with the basic features. Then I conduct regression with random forest feature selection on the basic data set. Then after that I conduct regression with random forest feature selection with the added features. Now we can move on towards looking at the results for the regression model. Here we can see the regression model results. We can see the regression model with basic features works best for gradient boosting regressor with an RMS value of 246.71 and an R-score of 0.98. However, regression model with time and lag features performs better as we can see that the RMS over here is 185.91 compared to 246.71, and the R score is also improved. This means that with more features we are able to explain the variance of the target variable more and in a better way. So regression model with time and lag features is performing better than regression model with basic features. Further on, we can look at the result of basic features with random forest feature selections. So the features that have been selected from the basic data set are customers, open, promo, day of week, school, holiday. We can see that gradient boosting is still performing better over here as well with the root mean squared error of 268.68. However, we can see that with the basic features, when we perform random forest feature selection, our accuracy has dropped from 246.71 to now 268.68. Furthermore, we can also look at the results with all features dataset where we have applied random forest selection. So basically from the all feature dataset, we have customers, open, promo, lag 1, day, lag 2, lag 3, month, day of week, year, day of week, number. So here we can see that gradient boosting regression is still working the best, and we have a root mean square of 218.73. With all the features combined for all the features, we had root mean squared of 185.91. So we can see that the accuracy has dropped, but the accuracy has not dropped by so much. So it is at our choice that we can look at random forest feature selection, because it might give us a model that is not very overfit. After performing the regression, we have performed the time series model. After performing regression, we move on to the vector autoregressive model for multiple stores. In this, we are trying to forecast the sales of multiple stores together. We tried with daily sample data and we tried with weekly sample data, so that we can see that which sampling is better for forecasting for this data. We will be looking at the results in a while. After the vector autoregressive model, we applied smoothing models. Smoothing models gave a reasonable forecast, and we are also checking for 2 other stores in order to make sure that the results we are getting are not only for one store. We are also checking 2 other stores to ensure that we are getting similar results. So here you can see the detrended data and the rolling mean, raw data and the rolling mean. We can see that there is this is an additive time series with the seasonal component. It does not have a major trend in it. So we check for white noise, as there is correlation between the lags we can there is a correlation between the lags, we can say that this is not a white noise series. These are the autocorrelation and the partial autocorrelation plots. So first we perform the simple exponential smoothing. So we get these are the results we are getting. So basically we can see that the simple exponential smoothing model with different parameters, with different values of the smoothing parameter, is giving us a level average for the sales. It is giving us an average baseline sales that will be followed for the next 6 weeks. So a simple exponential model is suitable for cases where we need to find the trend in data. As we do not have a very prominent trend, it finds a level which can give us an average estimate of the sales. Then we try the Holt exponential smoothing. So Holt exponential smoothing has identified a trend, and it is predicting on the basis of that trend. As we do not have an increasing trend generally, and there is a component of seasonality, this model is not forecasting really well for this data. Then we use Holt winter seasonal smoothing. Here we can see that reasonably it is able to capture the seasonal component as well as the ups and downs in the sales. It is not compared to the other smoothing models. Holt winter seasonal smoothing model is working the best for this data. After this, we tried the Serima model. So these are the first, we check for stationarity, and we can see that the series is stationary, so we do not have to make this series stationary. Then from here we need to find the parameters of the Serima model. We choose the parameters where the AIC score is the lowest, and AIC score is lowest for these parameters. These are the results that we get from the Serima model. After performing the Serima model, we move on to the Arima model. So these are the results that we are getting from the Arima model. So here we can see the results for the time series models. We can see that Serima is giving an root mean squared error of 1313. AR is giving the lowest root mean squared error, that is of 859.621, so that we can say for this a specific time series the AR model with the rolling window value of 33 is the best. This value has been decided by using the autocorrelation. The highest correlation is somewhere between 29 and 33, and after doing some grid search, 33 seems to be the best parameter for the AR, and it is giving us the lowest root mean squared error. These are the results for the vector autoregressive model. Here we can see that the root mean squared error is much higher than when we are individually forecasting the sales of each store. Plus we can notice a thing that the weekly sampling has a higher root mean squared error than the daily sampling. So for this data set, daily sampling for the next 6 weeks for forecast generation is the optimal sampling rate. Then we can also further see the exponential models. Simple exponential model on test and train. We can see that by increasing the smoothing parameter, our errors is increasing, and the best accuracy for this type of model we are getting for the default values. We can now look at the model evaluation in general. We can see that time series AR model is performing the best. Not only the error is less, but the residuals are uncorrelated and follow a Gaussian converging at 0. It is followed by Arima model, though error is high compared to. So to conclude, we can say that the AR model is performing the best. Not only the error is less, but the residuals are uncorrelated and follow a Gaussian converging at 0. It is followed by Arima model, though error is high compared to simple exponential smoothing, but the model is better because of the residuals are minimized better in Serima. Just provides a level average. Simple exponential smoothing just provides a level average value, not a suitable model for this data. In smoothing model, only the Holt winter seasonal smoothing model provides reasonable results. Regression in general provides better results than time series. In the regression model, gradient regression boosting with time and lag features gives us the best result. Gradient boosting regression performs well, as we know, as it does avoid overfitting and combining many weak learners. By optimizing the error gradient, it is able to optimize the model bias. To conclude, we can say that both problems can be best solved with regression model, as mentioned in the results. To conclude, both problems can be best solved with regression, as we have seen in the result tables. However, that said, the time series model can give us a very good general view. The errors of regression are very minimal, so predicting the sales can help manage the inventory in an optimal way, avoiding over and understocking and optimal use of resources. Help in production planning, knowing that a promo is likely to trigger demand. Also in stores where there is a promotional offer, consumer spending is higher, so in order to boost sales of existing customer base, promotions can be applied. Constantly, new sales data needs to be incorporated in the training of the model if new data is also being fed. So any change in consumer behaviors will be detected in time by the model and will update its parameter according to the new behavior, this eliminating the chances of wrong predictions. So thank you so much for following this video. I hope you will find this work useful for your research or for your business problems.